All right, we're going to keep working on section 6.1 today. What we're going to look at is continuing the slope fields, particularly the sketches of those particular solutions. I'm really kind of disappointed about this today. I had a really nice kind of discovery worksheet for you to work through. The blank notes that I'm filling in here are a PDF file in the chapter 7 folder of notes on plus portals. So that if you want to print that out and write directly on that, you can. We're going to keep working with our differential equation x plus y. I'm going to say that there's an initial condition of f of 2 is 0. So here I have a slope field a little bit different from the one we filled out yesterday. With right here, my initial condition f of 2 is 0. So then if I wanted to go ahead and sketch in a curve for that particular solution, well, going to the left, we're going down, and as I get further, it's going to start flattening a little bit. As I go to the right, it's going up, but it's going to be getting steeper. And so one of the reasons we like having sketches of particular solutions would then be we can make approximations for that particular solution. So if I want to approximate what f of 3 looks like, well, I know 3 doesn't show up on my graph, but I can see it's getting steeper and steeper. To me, it looks like f of 3 is going to be about 3. It may be a little bit above, maybe a little bit under, but about 3 based on my sketch. Now, the issue here is most likely if you drew your sketch, you probably have a different f of 3 approximation than I do. You're close, but it's doubtful we have the exact same ones. And so we need some way of making this so that everybody can get the same approximation, so that when this is done mathematically, any mathematician can go through steps and get to the same result as you do. So the way we do this is we use the slopes of each point. And instead of making it say, well, I know what f of 2 is, because we were told it's 0, instead of going directly to f of 3, we kind of take baby steps and do a little bit, make an estimate there, do a little bit closer, do another estimate, do a little bit closer, do another estimate. So that way it's smaller steps to get to f of 3 instead of one big step. So we're going to say that delta x, and delta of course means change, is 0.2. So our x's are going to go up by 0.2 each time. And we're going to start with the 0.20. So to do this, we need to know what's dy dx at that point. Well, since it's x plus y, dy dx is equal to 2. So our new x is going to be the old one plus the 0.2. So my new x is going to be 2.2. To figure out my new y, I need a change in y. Well, this is where the estimating comes in. Because dy and dx are differential, standing for changes in y and x. So if I do dy dx times delta x, dx and delta x aren't exactly the same, but they're close enough that we can say for an estimate, we can cancel those out. So if I take 2 times, that was my dy dx, times my delta x of 0.2, I get dy is 0.4. So my new y is going to be 0 plus the 0.4. So now I have a new point. Now this is an estimate. This isn't going to be exact, but it's a reasonable estimate. So that estimate is telling us that f of 2.2 is going to be about 0.4. Now I'm sure you've noticed we haven't got all the way to f of 3, but we've now got a method to get to another step. So what we're going to do now is we're going to go ahead and approximate f of 2.4, which if you notice is another 0.2 step for x. So my new x is going to be 2.4. Oops, sorry. Don't need that yet. So My x is delta y. I need dy dx at that old point of 2.20.4, which will be 2.6. My delta y is going to be this 2.6 times my delta x, which is going to be 0.52. So my new x is 2.4. My new y is going to be the old one, 0.4, plus the 0.52, so I get 0.92. And here is an approximation. So this is about f of 2.4. So then I'm going to go another 0.2 closer around the x coordinate to get for f of 2.6. So I need my slope at the old point of 2.4.92, which is going to be 3.32. My delta y will be this dy dx of 3.32 times delta x, which is going to give me 0.664. So now I've got a new x of 2.6. My new y is going to be the 0.92 from just above here, plus the 0.664, which is 1.584. And this is approximately f of 2.6. So then I'm going to do another 0.2 closer on the x coordinate. So I need dy dx at the point of 2.6, 1.584, which is going to be 4.184. I need the delta y, which is this dy dx, times delta x of 0.2, which is going to be 0.8368. So my new x is 2.8. My new y is the 1.584 plus my delta y, which is 2.4208. And this is approximately f of 2.8. So if you notice, we're getting very repetitive in our steps, but we're all able to do these steps, so we should all be getting the same answers. So finally, to get f of 3, I just need one more step of 0.2 on the x coordinate. So I need to find dy dx at 2.8, 2.4, 208, which is going to be 5.2208. Delta y is going to be that dy dx times the delta x, which will be 1.04416. So I now have a new x of 3, and my new y will be the 2.4208 plus this 1.04416, which is 2.46496. And this is the approximation for f of 3. It's not hard steps, but it takes space because it's repetitive and we have to do this iterative process. So it takes some time. But again, no individual step is difficult. The reason we like this is now all of us, no matter what, if we have this differential equation of x plus y is the dy dx, the initial condition f of 2 equals 0, and we're saying delta x is 0.2, well then f of 3, all of us would get an estimate of 3.46496 for f of 3. To kind of give you a place where this is all written down, this is what is called Euler's method, because again, Euler created this, because he pretty much did everything. This is a way of using the slope field to get a solution to initial value problem by doing little line segments. And in class tomorrow, I'll demonstrate that a little bit better. But the general process is we start at xy, which is our given initial condition. We use the differential equation to find dy dx at that point. We increase x by the delta x, and we are always given what delta x is. We never have to pick it, it's picked for us. Then to figure out what to increase y by, delta y is going to be the dy dx we found in step 2 times the delta x, which gives us our new coordinate. Well, now this point replaces the initial condition in step 1, and we repeat the steps. And we keep doing this until we get to the value that we want to estimate. These have all been ones where I've gone from the initial condition to the right on the graph. If we start at the initial condition and need to go left, all it means is delta x is going to be a negative number, but it doesn't change anything. A common misconception is that people confuse Newton's method and Euler's method. Newton's method estimates the zeros of functions. In other words, we're trying to figure out what x is, but we know that y has to be 0, and we use derivatives to estimate that 0. Euler's method estimates function values. In other words, we know what x is, and we use derivatives to estimate the y's. So they kind of work with opposite variables here.